Welcome back. Today is our second day in the classroom, and those of you watching later on cable or on DVD, this is still kind of in the review mode, prerequisite material. I'm going to try to let student questions pretty much drive today. Today is the last day we'll spend on this prerequisite material, even though some of what we do after that might be and hopefully will be prerequisite when we get to exponentials and logs, but we've kind of allocated specific time for that in the class on the syllabus. This is a check it out, see what is review for you, what is not. Let's talk about it. So the sections in your book are 1.1 through 1.3, and what did you encounter that you would like to make sure that we address for a moment or two today in class? Now, I have stuff ready, so when you're out of ammunition, I've got plenty up here. I've never really been at too much of a loss for words. You'll find that out this semester. You'll probably be totally annoyed with me and my voice by the end of the semester. Hopefully not, but you might be. Anybody want to start? Yes, sir.
In section 1.2, reciprocal functions.
Okay, reciprocal function. And how will that be? How will that play out in this course? Well, the idea of a reciprocal. You take the existing fraction, if it's not a fraction, put it in fraction form, put a 1 in the denominator, and basically flip it. Now you expect it to behave very, very differently. Their first example would be a function like y equals x, and its reciprocal, y equals 1 over x. Very, very different functions. This is a line. It's a polynomial. We'll talk a little bit about polynomials in general today. Polynomials are nice, smooth curves, very predictable, no abrupt changes in direction, no discontinuities. So everybody knows this in your library of functions. So we've got this nice, smooth. Now, it really isn't a dotted line. It is a solid line, but that's what it looks like. Y equals 1 over x is a very, very different animal and is not a polynomial. It's not a polynomial because the exponents need to be non-negative integers to be a polynomial. I'll address that later in class. That is x to the negative first, so that exponent is not a non-negative integer. It is a negative integer, so it's not a polynomial. So we would expect there to be some kind of corners or cusp or discontinuities. This does have a discontinuity. Where is it?
0.
At x equals 0, we've got a vertical asymptote. Hopefully that's a familiar term. So y equals 1 over x looks like this, right? That discontinuity and things that have discontinuity kind of create problems for us in a calculus setting. One of the things, I'll try to relate this to how we will see it when we see it again. One of the things we're going to talk about in here are slopes and how curves have slope. This solid line right here, as far as the slope, the nice thing about lines are lines have a fixed slope. No matter where you are, if you're here, the slope is 1. If you're here, the slope is 1. If you're here, the slope is 1. That's why it's a line, because they have a fixed slope. This has a varying slope, so it depends on where you are. And when you talk about the slope of a curve, most of the time you talk about the slope of a tangent line to the curve. Here is the slope. Here at this point, there's the slope. There's the slope of the tangent line at that point. So it has variable slope. Do these tangent lines have anything in common besides the fact that they're red?
The derivative.
Okay, they happen to be, some of you said you'd had some calculus. The derivative really is the slope of the tangent. More on that later, a lot more on that later. But we will talk about slopes of curves, namely the slope of the tangent to the curve. Aren't all of these negative? Mm-hmm. Negatively sloped? Mm-hmm. So let's begin to kind of get this picture going. If we have a negative slope, what does the curve do from left to right? What is this curve doing? Somebody said it.
Decreasing.
It's decreasing. Isn't this entire curve decreasing from left to right? Start over here, it's falling, right? Mm-hmm. And you say, well, it doesn't fall here. It's got a little intermission. Got to take a little break, a little popcorn. And now over here it picks up again. What's it do as it goes from left to right? It's decreasing. So this negatively sloped tangent line has some impact on the shape of the curve. It basically forces the curve to be decreasing. The other thing that we'll deal with in this class that is related to a reciprocal function is we will, when we get to differential equations, we'll deal with something called orthogonal trajectories. And when we get to orthogonal trajectories, we'll take a differential equation. Maybe it looks like this. And orthogonal means that they meet basically at right angles. The two things are orthogonal. So we will basically, for the orthogonal, we will take that and take its reciprocal and take, in fact, its negative reciprocal. What does that connotate to you if things have slopes that are negative reciprocals of one another?
Perpendicular.
They're perpendicular. So we kind of force them to be perpendicular. So there's another case where we'll use a reciprocal function. But I guess the authors are trying to kind of refresh you and review you on the fact that you can start with a pretty simple function and you take its reciprocal and all of a sudden it's very, very different. Not at all in the same classification. Anything else that anybody wants to address from section 1.1, 1.2, or 1.3? This is actually a good sign that it's kind of quiet. I mean, it means that this, for the most part, is review for the entire class. So that's a good sign. Yes, ma'am.
Composite function.
Composite. Okay. So composite functions. Where did you find that? 1.1?
No.
1.1?
Oh, it's
1.3.
yeah, 1.3.
1.3?
Page 44.
44 in this text. So composition of functions, so composite functions. We're not always so lucky to have a simple function. We kind of have a function within a function. So it's nice and clean and wonderful when it is the sine of x. So we take this x value that is in the domain. And by the way, what's the domain for the sine function?
All real.
All reals. You can take the sine of any number you want to. And when in doubt in this class and any other subsequent calculus class, use radians. Okay? If you have a choice between degrees and radians, always choose radians. It's kind of a unitless description of rotation, so it doesn't carry any baggage along with it. So if we have the sine of x, we can put anything in there for x and basically come up with a set of points, a table of values, a graph, a picture of sine of x. But we might, in fact, not just have the sine of x. We might have a composed function, where the first function is to add pi over 2 to the angle. Once we've done that first function of adding pi over 2, the second function is to take the sine of that angle. So this is a simplified version of this, and it can get a lot more complicated than that to get a composed function. So we could have the sine squared of x plus pi over 2. So what do we do first? We add pi over 2 to the angle. There's our first function. What's the next thing we do? We square it. I'm sorry, we take the sine of it, right? So there's our second function, is taking the sine of it function. And the third function is to do what? Square it. So there's really kind of three functions. When we get to calculus, and you're not responsible for this yet, but I'm telling you why this is important for you to hang on to and review. When you get to taking a derivative that is a composed function, it forces us to use another rule called the chain rule, because you have functions within functions, and you kind of have to keep deriving till you get to the innermost function. So if we have, for example, that the f of x is x squared, the g of x is the sine of x, and the h of x is x plus pi over 2, what would the composed function be that is the f of the g of the h of x? That's too many, right? That's too many in the composition. That doesn't even sound good. But we can do it. What do we do first to find the f of the g of the h of x? What do you start with? The h. So you're going to start with the h of x. Once you take the h of x, what do you do next? Take the g of that, right? And once you've taken the g of the h, then you get to this outermost outside function, then you take the f of that. So let's do that for these three functions. Does that look familiar, by the way, these three functions? I hope we'll get to a familiar place when we're done. What is the h of x? X plus pi over 2. So that's the first thing we do. Add pi over 2 to this independent variable, x. Now we need to take the g of that. How do you take the g of something? To take the g of something, you take the sine of that something, right? Well, what is our new something? X plus pi over 2. So the g of that would be the sine of x plus pi over 2. And now we're going to take the f of that. What do we do in the f function to whatever it is we throw in for the domain? We square it. So the final is sine of x plus pi over 2 squared, which happens to be the same thing as that, right? A little different notation. So you can have a composition. You could have this whole string of functions. So we've got this composed function. So we're lucky when we get simplified functions. It's not necessarily awful, but it takes a little more care and caution when we have a composed function, depending upon how many things are in that composition. Does that suffice with that? Mm-hmm. Yes.
And
Wait just a second. Is it about this?
Yeah.
Okay,
also
go ahead.
This with yesterday. So the x plus pi over 2 would translate the origin to the left, pi over 2.
That's correct. That's correct. So, yeah, that's what I said I would start class with today. Okay, somebody said you were going to start class with something. We had something yesterday about shifting left and right. Anything else about this before I take this one away? How about domains? That's what I want to address real quickly before I take this away. How do you work the domain of a composite function? The domain of this was all reals, right? We talked about that? You can take sine of anything. What's the domain here? What do you have to be careful of? Well, you're doing three things now. You're adding pi over 2 to something. Does that restrict the domain in any way?
No.
Can you add pi over 2 to anything you want to?
Mm-hmm.
Yes. then what are we doing? Then we're taking the sign of something. Does that take what we now have as all reals, and does that add any restrictions?
No.
Can you take the sign of anything you want to?
Yeah.
Yes?
Okay.
And now we go back into the outermost function, squaring function. Does that add any new restrictions? Can you square anything you want to? You can square anything you want to. So we're also going to have all reals. But you do have to track it backward, starting with what you do first, what you do second, what you do third, to see if you've got any restrictions on the domain. All right, to take this away. All right, this was addressed yesterday, so mainly the top part of this is what was addressed. If you just have the plus c after you've taken the f of x, that takes this f of x curve and picks it up and lifts it up and slaps it down c units up, right? If you have a minus c, that takes this y equals f of x, lifts it off the paper, slide it down c units, and slap it back. Same exact shape. This is what was addressed yesterday. And I kind of said this in words, but I knew this would do a better job. This is similar looking to these two things above, but is different because now you're taking x minus c and throwing it into the function, just like we just did with x plus pi over 2. That has a different effect than this does, either one of these above it. So the x minus c causes it, the net effect is to shift it to the right. Why to the right? Because you're subtracting c from every x, so things happen more slowly. More slowly, graphically, is to the right. If you add c to x before you put it into the function, that has a net effect of taking that same shape, that same function, and picking it up and moving it to the left. So that, I think, probably does a better job than what I did yesterday of explaining that in words. So they look somewhat similar, but they are distinctly different. All right, anything else from 1.1 to 1.3? Yes?
It's actually a question from WebAssign, but you're given f of x and g of x, and you find g of f of x. And I was also asked how to get the domain, but I don't understand how the domain's not all real numbers.
Okay.
F of g of x is square root of 2x plus 3.
So they give you the composed function?
Yeah, they give you both, and then you put it together.
So the f of the g is?
F of g of x is square root of 2x plus 3, and all of that is squared.
So 2x plus 3 is under the?
It's g of f of x. I'm sorry. It's okay. No, g of f of x. And under the square root is 2x plus 3, and the square root is squared.
So this is squared?
Yes, all of that is squared, and then plus 1.
Okay.
And it says find the domain.
So we don't know we don't know the f of the g?
Yeah, f of g is 2 is under the square root.
Is what?
2 parentheses x squared plus 1 close parentheses, and then plus 3. Well, that's under the square root too.
That's under the
Yeah.
square root? Okay. I'll bring my WebAssign from now on so we don't have translation issues. Sorry, that's my fault, not yours. And then what are the questions? What do they ask you to do?
Finding the domain of g of f of x.
Domain of this one.
Yeah.
I'll use that a lot, that little reverse question mark. I was a Spanish minor. I love that about the written Spanish language is you can tell that it's a question when you start to read it. And in English, you never know it's a question until you get to the end. You know, it could be this long sentence, and at the end, it's got a question mark. You didn't know that until you get to the end. In Spanish, you know that when you start it. So what is the domain? Well, let's go inside, kind of to the innermost function. Well, what is the innermost function?
2.
Okay, we're going to double x and add 3. Can you think of any restrictions there? Can you think of a number that you cannot double and add 3 to it? That's all real. So we're okay so far. No restrictions. What's the next thing?
The square root.
Is the square root. Now we're going to get a little bit of an issue, right? Because you can't take the square root of any old thing. So far, we're all reals. Now we're going to take the square root. So we better make sure that what is under this radical is what? Positive or zero. Okay, so non-negative, right? So now we're going to get some restrictions. So 2x plus 3 has got to be greater than or equal to 0. Is that okay? So, I mean, just kind of talk through it. It doesn't have to be, math doesn't have to be this whole memorized thing that you say, look at that, and I either know how to do that or I don't. Well, just kind of talk yourself through it and say, well, I'm taking the square root. Can I take the square root of anything I want to? No, you're not allowed. With real numbers, you're not allowed to take the square root of a negative number. So we've got to make sure we don't get one of those. So let's make sure whatever is under here, however ugly it might be, let's make sure it's greater than or equal to 0. So let's do that. How do I do that? Subtract 3 from both sides. Divide by 2. Now, you do have to, with inequalities, if you're dividing through by a negative, that reverses the order of the inequality, right? Multiply or divide by a negative. We didn't do that here. So x greater than or equal to negative 3/2. So we've kind of followed through on that restriction. As long as we choose our x's in this area, we're safe. Now let's go further. What's the next thing we do? Now that we've chosen x's from this area, what's the next thing we do to the variable quantity? Square it. As long as we choose our x's here so that it is legitimate square root, it is a real number, can we square those? Yes. And then the last thing we do is add 1. That's not going to create any new restrictions. Now, one of the things, so we've got x greater than or equal to negative 3/2. Do they ask for interval notation?
Well, inclusive and non-inclusive.
Okay.
Yeah.
So greater than or equal to negative 3/2. So negative 3/2, either infinity or positive infinity.
Positive infinity,
right?
yeah.
And we'll use a parenthesis there because we don't have an endpoint when we talk about infinity. If you see a bracket, that means it stops somewhere. Parenthesis means it doesn't stop at any specific location. Now, and you may have another question,
Yeah.
but what could this be? I mean, they could go ahead and say 2x plus 3 square root. Let's square the square root. What do you get when you square a square root?
2x plus 4.
You just get 2x plus 3, and then you'd add 1 to it, which would be 2x plus 4. Now, if you look at this version, that doesn't appear to have any restrictions, right? So you can't necessarily look at the final destination. You have to look at how you get there in a composed function setting. So this right here, if you write it like that, that doesn't have any restrictions. But when it's written like this, and kind of how you work your way through that composed function, it does have restrictions. Is that what your question, your issue was?
Yeah, that was
Okay.
mine. Yeah.
Yes, ma'am. I'm going to learn names, but I just got the seating chart today, or I don't even have it yet, but I'll learn names so I don't just have to point and say yes, sir, and yes, ma'am.
If you were to find the domain of f of g of x, would you go about setting underneath the square root equal to 0 and solving that equation too? How would you go about finding
Oh, the other one?
Yes.
Yeah, I would probably start inside with kind of the innermost function, which is right here. The outermost function is the square root function, so I'd save that to the end. So it looks like the first thing I'm going to do to x is squaring it and adding 1, right? No restrictions? All reals? The next thing is doubling that result and adding 3. Any new restrictions? You can double anything you want to and add 3 to it. Now I get to this last restriction. I'm taking a square root, so I've got to make sure that what is under this radical
This is positive.
is greater than or equal to 0, right? So that's kind of the last line of restrictions on that problem. What do you think? 2x squared plus 5, will that always be greater than or equal to 0
Yes.
for any x that we plug in?
Yep.
Right? You're going to square it, that's positive. Double it, still positive. Add 5 to it, still positive. So we don't have any restrictions on that at all. Is that okay? Anything else? We're getting there. We're getting a lot of things reviewed today. I've got a lot more. Anybody else? I want to make sure your questions get answered first before we do a quick run through of some topics that maybe we haven't covered yet. Okay, yes.
It's another web assign question.
Okay.
Okay, you're given the area of a area of a rectangle is 19 meters squared.
Okay.
And it says find the formula of the perimeter of the rectangle in terms of x.
In terms of what?
In terms of x, or it really didn't matter. just
So the
didn't
area
know.
of the rectangle is 19 square meters.
Yes.
Find the formula for the perimeter of the rectangle. And what?
In terms of x.
In
I
terms-
guess it didn't matter. I don't remember exactly what it said. It just said find the formula of the perimeter.
Okay. We may use other letters here, but since you don't really have it with you. Does anybody have it with them, the web assign? I need to bring a copy of that. All right, so area of the rectangle. So let's see if we can kind of go with a picture. I don't know. We don't know that it's a square, so we can't assume it's a square. So we'll assume, it might be a square though, right? But we can't assume that because not all rectangles are squares, even though all squares are rectangles. Is that right?
Mm-hmm.
So let's say base and height, okay? And with the given fact the area of the rectangle is 19, we know what is true.
HB equals
Okay, b times h is 19. Now, the perimeter, in terms of b and h, would just be b plus h plus b plus h, right? So 2b plus 2h. I have an idea they want you to, and there's a purpose for this. To this point, it seems like, actually, that seems like a 6th grade problem. But now it begins to be helpful for us in this course, is let's not give the perimeter in terms of both letters. Let's give the perimeter in terms of one letter. So I don't care which one you solve for. Let's say that h is 19 over b. Then we can make this substitution. Wherever you see an h, we'll plug in what h is equal to, which is 19 over b. So it's twice the base plus twice the height, but the height is known to be 19 over b. So twice 19 over b. If you double a fraction, you double its numerator. So that will have some carryover. And some of you have had some calculus. When you do an optimization problem or a max-min word problem, one of the steps is to reduce the equation, however many variables you have. You could have 3 variables, reduce it to a function of 1 variable. So this will have some carryover. Anything else? All right, if you come up with something, if what I say the rest of the class today triggers something in your mind, just stop me and we'll try to get your question answered. All right, so I'm working right now in 1.1. So let's take this. This is a composed function. The innermost function is subtracting 5 from x. The outermost function then is taking the square root. So what we just saw is that we've got to make sure that x minus 5 is what? Greater than or equal to 0. So hopefully, based on what we've done already today, we've got a restricted domain, everything 5. Now, it's handy, I think, if we were weathercasters, if we were meteorologists, and you paid attention to all these computer models, and they've got this storm that's going on in Florida now, and it's going to, come back and hit Florida again for the 3rd time. I'm sure they're loving that. Those are all, and they can kind of predict that with computer models. But if I were a weathercaster and a meteorologist, occasionally I'd go look out the window, to see, is it raining? We predicted it to rain, but is it actually falling? So let's look out the window here, and we've got the algebra that solved this. Does that make sense? As long as we choose a value that's 5 or more, we're going to get a real value out of the square root of x minus 5. Well, try a value that's not greater than 5 and see if it causes a problem. Try 4, 4.9, 4.99. That's a problem, isn't it? Mm-hmm. We're trying to take the square root of a negative number. And I know in certain math classes you've addressed the square root of negatives before, but we don't want to mess with them in this course because they're not real. So if it's not real, we don't want to deal with it. So don't forget to just take a few seconds to see if that answer is reasonable when you come up with an answer. Okay, here's a rational function. A rational function has a polynomial in the numerator. That's a pretty simple polynomial. And a polynomial in the denominator. And polynomials in and of themselves will always be continuous and smooth curves. A quotient of 2 polynomials, not necessarily the case. In fact, we've got problems with this one, right? Mm-hmm. Where are the problem values? In the denominator, we've got to make sure x never takes on what value or values?
0.
X can never be
2.
2
or negative 2.
nor negative 2. So those end up being what for this picture?
Zeros.
Not zeros. A 0 is where the graph hits the x-axis.
Asymptotes.
Asymptotes. So we come over here to negative 2 and positive 2. And those become vertical boundaries for this graph. You'll never have a point plotted in them. And in fact, more than that, what else happens near one of these vertical asymptotes?
Graph curves.
It goes kind of crazy, doesn't it? Either way up toward positive infinity or way down toward negative infinity. So this has 2 vertical asymptotes. This picture also has a horizontal asymptote. Be interesting to see where we go with this. I don't know how fair of a question this is on the second day of class. Anybody want to tell me where the horizontal asymptote is and how you came up with that?
First you gotta substitute the x and y and switch them almost and get a reciprocal thing.
You could. That's a way. You could find the inverse and then find the vertical asymptotes for the inverse. Those would be horizontal asymptotes for this. Does that make sense?
Yeah.
Yes? And we'll get to some inverses. That would work. Another way is to see what happens as x gets infinitely large in this function. Can you picture that? You keep putting larger and larger and larger values in for x. What happens to the y values on this function? Yes, sir.
As x gets bigger, you're making the number on the bottom larger. So
Okay.
it's dividing 4 by a larger number, so it's approaching 0.
There we go. Everybody follow that all right?
Yes.
You don't need me in here. We'll just kind of let you answer each other's questions, and I'll just moderate. That's exactly right. You keep putting in larger and larger values for x. The numerator's fixed. I don't care if the numerator's 4 trillion. Isn't the denominator eventually going to get larger than the numerator?
Alright.
And eventually, when that happens, the value of this tends to 0. So as x approaches 0, x approaches infinity, g of x approaches 0. So we do, in fact, have a horizontal asymptote on this picture as well. Now, they're different animals, vertical asymptotes and horizontal asymptotes. A vertical asymptote never has been crossed, is not going to be crossed today, and never will be crossed. You'll never have a point in a vertical asymptote. Horizontal asymptote is different. It's only good for very, very large values of x. So it is possible if when x is small, and I don't know what small is, I know it's not huge, but when x is small, you could actually plot a point that x could be, the y value could be 0 for some small value of x. So they are boundaries, but in this case, it's only a boundary for large values of x. So we could plot points on this, but we don't expect the graph to be continuous, right? We expect it to be broken at -2 and 2. And eventually for it to do something like this, either come up to the x-axis from underneath or do this, right? That's how it's going to approach that boundary as x approaches infinity. This got mentioned but not really addressed in detail yesterday. Is that better than my script?
Yes.
I knew that. Vertical line test for a function. That got mentioned because I had 2 points, 1,5 and 1,8. They were in the same vertical line. The x value 1 was assigned 2 different y values. Therefore, it wasn't assigned a unique y value. Therefore, it wasn't a function. So this vertical line test, what is the big deal about things being functions? Why do we want them to behave as functions? Let me see if I can give an Olympic example. Of course, the sprinters this year are either Jamaican or from the U.S. Of course, all those Jamaican sprinters have all gone to U.S. colleges. I think that's kind of interesting that we're training all the athletes from all around the world in our country. That's pretty interesting to me. Most of them, anyway. So in the 100, I think, didn't the Jamaicans sweep the 100 in the men, right?
Yeah. Section right.
Okay. So let's say, I'm going to put something somewhat artificial here, but I'll relate it to that situation. So, and Usain Bolt won, right? He won the 100.
I think so.
Usain, and he won the 200 last night? Okay,
I'm not sure.
so he's in lane 3, okay? And he runs what was his time? I'll make up a time. 9.69,
Sounds right.
okay? Now, in this race, in the 100, he won the gold medal at a certain time, okay? So he's lane 3, that's his time. It just so happened in this race that the 2 other Jamaicans who won the silver and the bronze, they tied, okay? They ran exactly the same time. Is that humanly possible? It is.
Yeah.
With the accuracy that they're using on the stopwatch, lane 4 ran a 9.82 and lane 5 ran a 9.82. That's possible. Not only possible, it happened. They tied. Would this be possible in this little set that I've got going?
No.
Could lane 3, the winner, could he have run a 9.69 and also in the same race run a 9.62?
No.
No, I mean, that's ridiculous. He's got a time that's associated with that lane, right? It's not 2 times and you get to pick one at the end. So 3 is assigned a unique y value. Does that make sense? This is absurd to think that the runner in lane 3 for that one single race could have 2 different times. Now, here lane 4 is assigned 9.82. Is it a problem that lane 5 also is assigned 9.82? That's not a problem. That's still a function. What would be a problem? It would be a problem if lane 4 were assigned something else other than 9.82. That's a problem. So it's okay to repeat y values in a sense, right? You can have points in the same horizontal line, but we can't have points in the same vertical line. That would really make our world confusing. You go to take your item up to the grocery store checkout, and you know how they all have those little universal product codes, right? And they scan it. So it's, I don't know, it's celery, okay? You've got this bunch of celery. There's its UPC. And it spits out on this device. It's either $1.49 or the very same bunch of celery is $32.98. Okay? Don't want to check out at that register. There's a problem there. Okay? Because I may be forced to pay this when actually the price is this. See the problem with 2 different y values assigned to the same x value? That our world just doesn't work that way. So when we're trying to use, I know this sounds a little corny, we're trying to use mathematics in a lot of ways to model things in the real world. They're functions for the most part. Things in the real world are functions. You project an object up into the air. Okay? After 3 seconds, it's 145 feet, and it's also 10 feet off the ground. Don't think so. Don't think that's possible. It can't be 2 places at the same instant. So we want things that are functions. Now, so one of these is bad, so I cross that out. Could it be 145 feet off the ground some earlier time or some later time? Yeah. Maybe it's 145 feet off the ground on the way up, goes further, reaches its peak, and at 5 seconds, it's also 145 feet off the ground. That's possible. So we can have that repetition of y values, but the repetition of x values, that's going to create a problem. So functions are a big deal. So the vertical line test is important. Piecewise functions usually create an issue. Probably get 2 more topics today. So I'll refer to those a lot as a split domain function because that's what we're going to do. We're going to break up the domain. So I'm just going to make one up. So it could be a 2-liner or a 3-liner, or it could be a lot more than that. But we've got a multiple description of this function based on different pieces of the domain. So let's say it's pretty simple. Let's say it's linear for a certain piece of the domain, and let's say it's for values a little bit larger than 1, it is some quadratic. So we've got linear for a while. Other than that, it is quadratic. So let's plot a few points and see what we get. So in the first set, I have to be careful that I choose values that are 1, which it is legit to pick 1, right? Or less. So when x is 1, which is legal, what's the corresponding y value? 3. And we kind of keep going back. It's linear, so we really just need a couple of points. 0, what? 1. That's probably enough. It's a line. So let's go to this one. Now, here's what I normally do. I kind of border on breaking the rules a little bit, but then I remind myself that I broke the rule. I don't have to go to 2. In fact, the value, the first legitimate value, is right on the other side of 1. Is that correct? 1.00000, bunch of zeros, and then 1. So what I usually do is I put 1 in there, and then I do a little reminder to myself that I'm going to delete that point. It's going to be an open circle. I want to go all the way up to that point, but I don't want to include that point. So if x could be 1, what would the corresponding y value be? 4. Okay? Not including that point in this set, but I want to go all the way up to that point. Now I can pick values larger than 1. Let's do that. If x were 2, what would we get? 1. If x were 3, 0, and x is 4, back to 1. So we've got this parabola that's shifted 3 units to the right. All right, so 1, 3 is included. 0, 1 is included, and then we can kind of figure out what this thing is doing to the left. Now I stop it at 1 because it's only that piece of the function, of the piecewise function or the split domain function, is only valid for values that are 1 or less. Now what works for values larger than 1? Well, 1, 4 almost made it, but it didn't quite make it. So that's an open circle. And the rest of these points I can include. So it's linear for a while, quadratic for a while. Is this a function?
No. Yeah. Yes.
It is. It almost fails that vertical line test right here at x equals 1, but the fact that this includes that point and this excludes that point kind of saves us. Yes, ma'am?
Isn't that jump discontinuity?
That is jump. It is discontinuous. That's true. And as a way of describing different types of continuity, we had one a while ago that was infinitely discontinuous when it went to that vertical asymptote. This is sometimes called jump discontinuity. The important thing is that it's discontinuous. That will create some problems for us in a calculus setting. All right. There's still some things that I didn't get to, but I think in a matter of about 5 minutes, maybe 10 minutes in tomorrow's class, I think we can sufficiently talk about all the main topics in 1.1 to 1.3. So we will tomorrow get to what is so-called material on the syllabus that potentially might be new material. See you tomorrow.